Okay, in this lecture we're going to talk about binomial experiments. And we start out by defining a Bernoulli experiment. A Bernoulli experiment is a statistical experiment that has the following characteristics. Okay, there are two possible outcomes, and we label the outcomes success or failure. The probability of success is fixed to be a number p, and that number, of course, being a probability, is between 0 and 1. So some examples of this. So flipping a coin is either heads or tails, and either heads or tails could be labeled as a success, just depending upon how you want to look at it. The probability of success in a fair coin is a 0.5. Rolling a single die and having it turn up as a 6. Okay, that's a binomial experiment because it can be either a 6 or not a 6. It's a matter of whether we frame being a 6 as a success or not. Okay, and so the probability of the success in this experiment is 1/6. Okay, because the 6 only comes up 1/6 of the time. If we have a jar that has 700 red beads and 300 blue beads, then pulling a single red bead from that jar is a Bernoulli experiment, because there can be only two outcomes. It can be either a red or a blue, and the probability of red, if we label red as success, is p is 700 out of 1000, or 0.700. So these are all examples of Bernoulli experiments. Now, a binomial experiment with n trials and a probability p of success, okay, consists of n independent Bernoulli trials, or n independent Bernoulli experiments, each of which has the same probability p of success. So we could get the same can that I described in the slide before, with 700 red beads and 300 blue beads, and pull out a bead and put it back and do this, say, 10 times. That would be a binomial experiment, okay? And a binomial experiment with 10 trials and a probability of 0.7 of success, okay? Since each trial is a Bernoulli experiment, its only outcome is going to be success or a failure. Now, if we write X twiddle BNP, this means that this is notation that means that X is a Bernoulli is a special random variable associated with the binomial trial. It counts the number of successes in your binomial experiment. Okay, and we denote, okay, px equal little x is the probability that this experiment has x successes. Okay, let's look at that a little bit. Okay, so we have a formula for this. Go back. Okay, this formula is when we have a binomial random variable like this. The probability of success is, okay, n choose x, and I'll come back to this later, times p to the x power times p times 1 minus p to the n minus x power. Okay, so this is a complicated formula. Let's talk about it. Okay. This symbol that we use, this choose, is called the combination symbol. N choose X denotes the number of ways that N blanks can be filled in with X copies of the same symbol, and it's also denoted NCX, where these are both N and X are both subscripts of the C. Okay, so to kind of get a clearer picture of this, for the special case N equals 4 and X equals 2, let's have our symbol be the @ sign, filling in 4 different blanks. And so we can have it filling in the first blank and the second blank, the first blank, and the third blank, the first blank, and the fourth blank. And then if we don't have any, if we have the first one being blank, then we can have @ symbols in the second and in the third, in the second and in the fourth, and in the third and the fourth. Okay, and there are a total of 6 ways of doing this. Okay, so 4 choose 2 would be equal to 6. Okay, this combination formula, okay, this N choose X, we have a formula for it right here. Looks kind of scary, where this is read N factorial over X factorial times N minus X factorial, where this, in general, K factorial is K times K minus 1 times K minus 2. Then we do the 2 times 1. And so K factorial is read as K factorial. Okay. And so, for instance, I would have my 4 choose 2 be equal to 4 factorial over 2 factorial times 2 factorial. 4 factorial is 4 times 3 times 2 times 1. So 4 times 3 is 12 times 2 is 24. 2 factorial is 2 times 1. So this is just 2 times 2 in the bottom, which is 4. 24 divided by 2 is 6, which is what we got on the previous slide, just by working it out, showing all the different ways that this could happen. All right, so the mathematical justification of the binomial formula. So I want to just show you by example. I think you'll get the gist of what's going on here. Let's say that we have a binomial experiment with 4 trials, and that I have 2 successes, and the probability of success is equal to P, which, yeah, I'm going to denote for reasons I'll explain later as capital P. That means the probability of failure is 1 minus P, which I'll denote as Q. Okay? And so here I show, as before, all the possible successes and failures. When I go over to this side, I'm going to replace the success by the probability of success and the failure by the probability of failure. And since each of these events are independent, because in a binomial the trials have to be independent from each other, the probability of this happening is the probability of each of these factors, capital P, capital P, capital Q times capital Q. And capital P, capital Q, capital P, capital Q, etc. as we go down here. But it turns out that when we do our substitutions, okay, that we get the same formula at each stage, okay, and this only depends on the number of successes in each of these experiments. Now, these are all of the things that can happen. They're mutually exclusive with each other, so the total probability of having these two successes we get just by adding these up, which will be, okay, 4 choose 2 times p squared 1 minus p, God almighty, squared. Okay, yeah, that not very pretty, but so you see, you just the number of different ways we can fill success in each of those slots. Count that up, and that will be the probability of that.